Welcome to the second lecture of two-port networks. In this lecture, we are going to study about T, pi, and lattice networks and solve them to find the Z and Y parameters, etc. And then we will see the combination of two-port networks, whether they may be in parallel or series or in a cascaded manner. And then we will see some examples about the two-port networks. Okay. So we have already seen T networks in the previous lecture. So this is how our T network looks. So let us find Z parameters for this particular network. If you see the input side, if we can write the KVL equation, we can write V1 is equal to, this current is I1 and this current is definitely I2. So we can write V1 as I1 into ZA. And you know that in this branch, the combination of I1 and I2 will be flowing. So we can write that in ZB, we will have I1 plus I2, right? Because both these currents are entering in this ZB branch. So rearranging this, we will get V1 is equal to I1 is taken common. We will have ZA plus ZB plus I2 ZB. So this is going to be your equation 1. And similarly, in the output section, if we write, we will get V2 is equal to, if we write KVL at output, we will get V2 is equal to, similar to the previous case, we will get I1 into ZB plus I1 plus I2 into ZC. Then this is going to be your equation 2. So you know that for Z parameters, you have equation V1 is equal to Z11 I1 plus Z12 I2 as your equation 1, and V2 is equal to Z21 I1 plus Z22 I2. This is your equation 2. So comparing 1, 2 and 1, 2 equations, we will get Z11 is equal to ZA plus ZB, Z21 is equal to, sorry, Z12, sorry, let us write first Z12. Z12 is equal to ZB, Z21 is equal to ZB, and Z22 is equal to, sorry, I think I have written it wrong here, little bit wrong. It will be I2 into ZB plus ZC, sorry. So Z22 will be ZB plus ZC. Okay, so these are the values of Z parameters you will get for any T-type network, this type of network. So if a network is given like this, you can directly use these formulas to find the Z parameters. So what I mean to say is that it would be easier for you to solve such circuits using Z parameters, right? Because it will be very easier to find all these Z parameter components. Now, if we see all these 4 equations and rearrange them, so we can find a reverse values, which means that ZA will actually be equal to Z11 minus Z12. ZB will be equal to Z12, which is basically equal to Z21, and ZC will be equal to Z22 minus Z12. So these values you can find just by using these equations of Z11, Z12, Z21 and Z22. So it can easily be calculated. So let us move to pi network now. So this is a kind of a pi network. Here you can see these values YA, YB and YC are not impedances, these are actually admittances. So this will be equivalent to 1 upon ZB, this will be 1 upon ZA and so on, right? So when you see that there is a current getting divided at the input and output terminals, it would be easier to see that two parameter network which employs KCL equations. So in which analysis you saw KCL equation analysis both had input and output, it was Y parameter, right? So it would be easier for us to calculate the Y parameter for this pi network, similar to the Z parameter that we used for T network. In pi network, we will be using Y parameter. So uh, if you want to write the Y parameter, what you have to find, you basically will have to find the KCL equation for input and output, right? So let us write the KCL equation. So KCL at V1. So this is the input voltage. I have taken this node as a reference node here, and this is our V1. So if this whole voltage is V1, this point will also be V1, and similarly this point will be V2 voltage, right? So applying KCL at V1, we will have I1 is equal to this current plus this current. Let me call it as I1 dash and this as I1 double dash, right? So is equal to I1 dash plus I1 double dash, which will be equal to what will be the value of I1? Basically V1 upon, suppose this YA value was 1 upon ZA. So suppose there was an impedance ZA here. So in that case, it would have been V1 upon ZA, but you know that you can call it as V1 into 1 upon ZA, right? So 1 upon ZA is basically equal to YA. So we can directly multiply this value YA here, which will be representing this I1 dash current, right? So just for making you clear, plus what will be the I1 double dash? It will be basically V1, this voltage minus this voltage. Remember the KCL equation, V1 minus V2 into YB. So YB is basically 1 upon ZB. Similarly, if we apply KCL at V2, we will get I2 is equal to V2 into YC plus V2 minus V1 into YB. Clear? Now rearranging this equation, this and this, we will get I1 is equal to YA plus YB into V1 plus sorry, it will be minus YB into V2. So this is going to be your equation 1. Similarly, I2 will be minus YB into V1 plus YB plus YC into V2. So this is going to be your equation 2. So on comparing this equation 1 and 2 with the standard Y parameter equations, which is I1 is equal to Y11 V1 plus Y12 V2, which was equation 1, and I2 is equal to Y21 V1 plus Y22 V2, which comes out to be equation 2. And on comparing these, you will finally get Y11 is equal to YA plus YB, Y21 is equal to Y12 is equal to minus YB, and finally Y22 is equal to YB plus YC, right? So this is how you will get all your values of Y11, Y21, Y12 and Y22. Now using these equation, you can definitely find the values of YA, YB, YC in terms of Y11, Y21. So you will get YA is equal to, using these equations only, you will get YA is equal to Y11 plus Y12, and then YB is equal to minus Y12, which will also be equal to minus Y21, and YC will be equal to Y22 plus Y12. So for any pi network, you can convert it into an equivalent Y parameter two port network. So let's go to the lattice network now. So this is a lattice network. We have already discussed a little bit about this in the previous lecture. So before we go on to solve the values of equivalent maybe Z parameter or equivalent Y parameter, we will have to assume one thing, that this network is a symmetrical network. Otherwise, the calculations will become very complex. So let us assume that this lattice network is a symmetrical network. Symmetrical means left, right, and up, down, both symmetry. So in that case, this ZA should be equal to ZD, and ZB should be equal to ZC, right? So if you want to calculate the Z parameter equivalent of this particular network under this condition, this symmetrical condition, in that case, if you see, if the ZA value is equal to ZD value and ZC value is equal to ZB value, so in order to calculate the KVL equations at the input, what you have to write, you have to first see that this current I1 which is entering, since the summation of this ZA and ZB will be equal to the summation of this ZC and ZD, if this output section is open circuited, right? Because in all the cases when we calculate Z11, what was Z11? It was V1 upon I1 when I2 is equal to 0. So in that case, when you have assumed I2 is equal to 0, that means you have taken this output as open circuit. So this branch, this circuit will be looking like this. This goes like this. And the other branch will be going like this here. So you see that there is one branch, this current I1 is going to be divided into two parts here, and the first one is ZA, and you already know that ZA is equal to ZD, so this is also going to be ZA, and then this other one is ZC. So since ZC is equal to ZB, as for symmetric network, I will be taking it as a ZB, and this also is again ZB. So you see that for the first branch, the whole impedance is ZA plus ZB, and for the second branch also, the whole summation is ZB plus ZA, which is same. So this means that this current is going to be divided into exactly two parts here, I1 by 2, I1 by 2, in these two branches for the calculation of Z11. So what was Z11? In the open circuit output condition, it was V1 upon I1, right? So all you have to do is you have to calculate this voltage V1 for any branch, for any KVL. You can write the KVL equation for any branch, because the voltage is going to be same in these both of these parallel branches. So if you write KVL equation, what will be happen? V1 is equal to I1 divided by 2, because I'm taking one half branch, multiplied by obviously ZA plus ZB. So what will be the value of V1 upon I1? And remember, this condition is I2 is equal to 0, because I have taken output as open circuit. So V1 upon I1 at I2 is equal to 0, which is nothing but Z11 will be equal to ZA plus ZB divided by 2. So you got the idea. This is how we will calculate these Z parameters for this circuit. So I'm just going to write all these values, and you can later, using the definition of these Z parameter value, you can verify it. So for this particular lattice network, which is symmetrical in nature, we will have Z11 equal to Z22 will be equal to ZB plus ZA divided by 2. And remember, ZA is equal to ZD and ZB is equal to ZC. We have already taken this into consideration. And also Z12 is equal to Z21. It will be equal to ZB minus ZA divided by 2. So this is you are going to get for a network like this, which is symmetrical, all your Z parameters. So let us make a lattice network which has admittances in place of impedances and calculate its equivalent Y parameter. So in the case of admittance by lattice network, we can find the Y parameter. And how to find it? Let us calculate Y11, which is basically equal to V1 upon I1 when I2 is equal to 0. Sorry, V2 is equal to 0. So if you want to take V2 is equal to 0, you have to short circuit this, and your circuit will become like this from the input side. And also you know that for symmetric network, you have assumed YA is equal to Y2 and YB is equal to YC. So you will have a network like this. So this is the point. Suppose I'm calling it A and B. So this is the point which is short circuited. So this point was A and this point was B. So this was got short circuited into one point, right? And so you can rearrange the above circuit like this. And this was your YA and this was your YC, but since YC is YB, I'm calling it as YB. And again, this was YD, so I'm calling it as YA because YA is equal to YD, and this also as YB. So you can see that this voltage V1 is between these two terminals, and you have a current I1 entering here. So if you can rearrange this circuit, you know that in the parallel combination, admittance gets added. So just opposite of resistance or impedance. In impedance, you will have ZA into ZB upon ZA plus ZB. But if you have taken already the reciprocal, which is admittance, you can directly add them. So you will get like this. So this is your V1, the whole voltage. This is your current I1, and this is your YA plus YB, and this is also your YA plus YB. So when these two admittances are in series, if the impedances are in series, they are just going to get added. But if admittances are in series, the opposite going to happen, and it is a kind of a parallel combination of two impedances. So what you are going to get? You are just going to get like this: YA plus YB divided by 2. The series combination of two admittances is going to be like a parallel combination of two impedances. So this is your V1 and this is your I1. So you will get V1, V1 is equal to I1 into, since this thing is not impedance, so you have to divide this thing from I1 because V is equal to I into Z. So this is your admittance function. So you will have to divide it like this: 1 by YA plus YB divided by 2, right? So what will be the value of I1 upon V1? And remember, this whole thing is calculated when V2 is equal to 0, right? We have initially assumed this A and B as short circuited. So V2 was 0. So what will be the value of I1 upon V1? It will be, this thing will go here. So you will get YA plus YB divided by, sorry, let me write it here, divided by 2. And this thing when V2 is equal to 0. So what was this? This was nothing but Y11. So you get Y11 is equal to YA plus YB divided by 2. So similar to this derivation, we can find other values also. So we will get Y22 also as YA plus YB divided by 2. Everything is same, just it will be happening from the opposite side or output side. And similarly, we will get Y12 is equal to Y21 is equal to YB minus YA divided by 2. So these are the values of admittance parameters for the lattice network, which is symmetrical. And if we just use the opposite, using these 3-4 equations, we will find YB is equal to Y11 plus Y12, and YA is equal to Y11 minus Y12. So using these equations, we will get this. Clear? Now let's move to the combination of two-port networks, and after that we will be doing some examples. Now let us look at series combination of two-port networks. You may have a feeling that these two networks are in parallel, but they are actually not, because uh, if you see the input side, you see that this current I1 is entering this first network, and obviously whatever the current will enter, it has to come out from the other terminal of the same port also. So if I1 is entering from this whole network, this I1 should be coming out also from this terminal, right? Similarly, this I1 is similar to this I1 dash, which is entering in this first two-port network. So since this is the same line, this I1 must be equal to I1 dash. So when I1 dash is entering here, it should be the same current should be coming out here, and this I1 dash is the same current is entering this second port also. So for the second network, let me call this as network A and this call as network B. If the same current is entering two different network, then definitely they must be in series, because it can be said that they are in the same line, right? And output side also, the same current is entering and the same current is coming out here, because this I2 dash should be this I2 dash is entering here, this I2 dash is coming out, and the same current is entering as I2 double dash here, and this I2 double dash is coming out from here. So you can say that the same current is entering and coming out from this terminal outside, right? So we can say that these circuits are in series. So for series combination, it is always convenient for us to use Z parameter. You will see why. We can conveniently represent a combination of these two-port network as a single two-port network, which will be better represented by Z parameters. So let me call Z parameter of this network as Z11 dash, Z12 dash, Z21 dash, and Z22 dash network. And let me call this as double dash network, Z11 double dash, Z12 double dash, like this, right? So we know that I1 is equal to I1 dash, which is basically equal to I1 double dash, because the same current is coming and entering in both these input terminals. And similarly, I2 is equal to I2 dash, which is equal to I2 double dash. Now, can you tell me the relationship between V1 and V1 dash and V1 double dash? If you see, this V1 is nothing but the series voltage combination of V1 and V1 double dash. So you can say that V1 is equal to V1 dash plus V1 double dash, and also V2 is equal to V2 dash plus V2 double dash. So now let us write the individual circuits Z parameter equation. So for the first circuit, V1 dash is equal to Z11 dash I1 dash plus Z12 dash I2 dash, equation 1, and similarly V2 dash is equal to Z21 dash I1 dash plus Z22 dash I2 dash. This is your equation 2. Similarly, you can write the equation for second two-port network also. So it will be, so these will be the voltage equations for second Z parameter two-port network, and this was the first. So if you want to calculate V1, you have to do V1 dash plus V1 double dash. So what you are going to do, you are going to add the equation 1 and equation 3. And similarly for V2, you are going to add V2 dash plus V2 double dash. So you will be adding equation 2 and equation 4. So doing that, So we will get on addition of 1 and 3 and 2 and 4 these equations v1, and since i1 is equal to i1 dash is equal to i1 double dash and i2 is equal to i2 dash and i2 double dash, we have replaced all these i1 dash and i1 double dash with i1 and i2 dash and i2 double dash with simply i2. So we will get an equations like this for v1 and v2, right? So on comparing this with the standard equation, v1 is equal to z11 i1 plus z12 i2 and v2 is equal to z21 i1 plus z22 i2, we can see that z11 is nothing but z11 dash plus z11 double dash, z21 is equal to z21 dash plus z21 double dash. Similarly, z12 is equal to z12 dash plus z12 double dash and z22 is equal to z22 dash plus z22 double dash. So you can see that all these elements, so if I want to convert this circuit into a single two-port network whose parameters will be z11, z12, z21 and z22, let me write it in a matrix form. So what is going to happen is all these individual components are getting added. So we can write that for a series combination of network z11, z12, z21, z22, the combination, the z parameter of the series combination of two z parameter networks will be simply the addition of these individual z parameter networks. So this is what you are going to get for a series combination. So you just add these parameters and you will get the solution. Similarly, for parallel combination, let us see for parallel combination. Now, as you can see here, these circuits are in parallel combination. Why parallel? Because the current is getting divided from here in two parts for these two different two-port networks. So on seeing this, you can say that I1 is equal to I1 dash plus I1 double dash. Similarly, I2 from here is equal to I2 dash plus I2 double dash. And since these are in parallel, you see that this V1 is nothing but going to be coming here. And also this V1 double dash is also coming here. So we can say that V1 is equal to V1 dash, which is equal to V1 double dash. And also V2 is equal to V2 dash is equal to V2 double dash because of the parallel combination. So from general common sense, you can see that in series combination, we applied, it was convenient for us to use Z parameters. So in parallel combination, definitely where KCL equations involved, it will be convenient to us to find the Y parameter. So similar to the definitions and derivations, from where we find the series combination will result in the addition of all these Z parameter values. Similar to that, here also in parallel combination, we will get addition of Y parameters. So if I assume this whole thing as a single two-port network, whose parameters are y11, y12, y21, y22, we will get y11, y12, y21, y22 as equal to y11 dash, y12 dash. So similar to the previous case, in the parallel combination, we will have the equivalent y parameters as a summation of the individual y parameter of these two parallel two-port networks. So I'm not going into the derivation because similar to the previous case, you can go on, and even if you want to do, you can just check the book. So it is very simple to derive this equation. So let us go to the combination of series and parallel combination. So in this case, you see that input side has a series combination, but output side has a parallel combination. So what kind of parameter reminds you of this kind of a circuit? Where at input you can apply KVL and at output you have to apply KCL. So it was hybrid parameter. So definitely in hybrid parameter we have input as a series circuit and output as a parallel circuit. So let me call them as combination of two hybrid parameter network. Let me call them as H dash, which is nothing but the matrix of H11 dash, H12 dash, H21 dash, and H22 dash. And let me call this H double dash, right? And if you want to calculate the combination of this circuit, the whole combination as a single two-port network, let me call it as H parameter. So using the simple common sense we discussed previously, in the input side, if we calculate the KVL like V1 is equal to V1 dash plus V1 double dash and put all these two hybrid parameter values, we will get our H11, H12. So we are going to get a combination of hybrid parameter of these two series parallel circuits. So the final hybrid parameter will be equal to the summation of the individual hybrid parameter of these circuits, right? Because at input you have series and at output you have parallel. So now let us move to the cascade combination. So the combination that you can see on your screen is basically cascade combination, or we can also call it as tandem combination. So the two port networks are put back to back. So here you can see that this current I1 is basically equal to I1 dash, and you will see that it will be easier for us to represent this kind of a circuit using ABCD parameter as a whole combination. So if you want to make a single two port network, it would be easier for us to use it ABCD parameter. So let us write the equation of ABCD parameter for the first equation. So, sorry, the first two port network. So we will have V1 dash is equal to A. So we will have A V2 dash, let me call it A dash because I have taken as a dash two port network, minus B dash I2 dash. This is your equation 1, and I1 dash will be equal to C dash V2 dash minus D dash I2 dash. This is your equation 2. We can rearrange this equation and write it as V1 dash in the matrix form. You must have studied already this in your mathematics. I1 dash. So in the matrix form, this will look like this in the matrix form. A dash, let me write it as plus B dash only. B dash, C dash, and D dash multiplied by V2 dash and minus I2 dash. So let me call it as equation A. So this is your ABCD parameter for the first two port network. Similarly, for the second two port network also, you can write V1 double dash and I1 double dash equal to A double dash, B double dash, C double dash, and D double dash multiplied with V2 double dash and minus I2 double dash. Now, if you see this circuit, you can say that V1 is nothing but equal to V1 dash and I1 is nothing but equal to I1 dash. So V1 is nothing but equal to V1 dash and I1 is nothing but equal to I1 dash. And also you can see that V2 dash is nothing but equal to V1 double dash. So V2 dash is equal to V1 double dash, and also I2 dash is equal to minus of I1 double dash, right? So I2 dash is nothing but equal to minus of I1 double dash, or you can say that minus of I2 dash is equal to I1 double dash. So this also you got. And finally at the output side also, you can say that I2 is equal to I2 double dash and V2 is equal to V2 double dash. So what happens is, now you can replace this this thing V1 dash and I1 dash with V1 and I1, because these two things are same. And also you can replace this V2 dash and minus I2 dash with V1 double dash and I1 double dash, which is in turn the equation of this, right? So let me write it step by step. So what I'm doing is, in this first equation, let me call this as second, and this was my first. So in the first equation, I am replacing V1 dash and I1 dash with V1 and I1, and V2 dash minus I2 dash with V1 double dash and I1 double dash, obviously. So we will get V1 I1 is equal to H11 dash, H12 double dash, H21 dash, H22 double, sorry, single dash, all are single dash, dash dash, multiplied by, now here in place of, sorry, what I'm doing, I'm sorry, this is ABCD parameter, not hybrid parameter. A, B, C, D, dash, 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 dash. Okay, so now we will be replacing this thing with what? V1 dash and I1 double dash, V1 double dash and I1 double dash. So we will get V1 dash double dash and I1 double dash. Also, from this second equation, you have V1 double dash and I1 double dash as this, right? So what you will get, V1 I1 is equal to, now this will be like that only, A dash, B dash, C dash, D dash, and in place of this, I am going to replace this whole equation from equation 2. So it will be A double dash, B double dash, C double dash, D double dash, and now finally, in place of V2 double dash and I2 minus I2 double dash, I'm going to write this, since I2 is equal to I2 double dash and V2 is equal to V2 double dash. So I'm going to write it as V2 and minus I2, because here minus I2 double dash was here, so it will convert to minus I2, right? So you have a relationship between V1 I1 and V2 and minus I2, and in between you have got this thing. So you also know that for normal ABCD parameter, for a single two-port network, you will be having A, B, C, D, V2 and minus I2. So on comparing these two, what you will get? You will get the final ABCD parameter for a cascaded network will be equal to nothing but matrix multiplication of these two individual ABCD parameter. So you will have to simply calculate the matrix multiplication of the two individual ABCD parameter, and you will get the overall ABCD parameter for a combined network. So this is how you will use ABCD parameter for a cascaded network. So remember one thing, in the case of series combination, you were using Z parameter. In the case of parallel combination, you were using Y parameter combination because it's simply added. And in the case of hybrid, since at the input it was series combination, at output it was parallel combination, you will be using hybrid parameter. So the hybrid parameters got added. But in the case of cascaded network, you will be using ABCD parameter, and in place of addition, you will have to do matrix multiplication. So this thing you have to keep in mind. So if the question comes of combination, you will directly use this parameter for your answer.